It's now time, Carlos, to start with your presentation about ITER, the status of ITER, of course, first fusion installation with full nuclear license. I want to remark this point of full nuclear license in nuclear fusion by the first time.
Now it's working.
Please.
You can keep. Okay. Thank you, Manolo. And I want to thank certainly the organizers for this kind invitation to tell you about ITER, what is the situation with the project and so on. As you can imagine, for me it's a double pleasure. One, to be able to tell you the progress, which I think, and I hope at the end of the talk you realize that this project really is in its track to achieve all the goals that have been put, but also to be here. You know, Madrid is my hometown where my 2 out of 3 daughters were born, so it's really for me a very good opportunity to be here. So let me tell you, let me see if I know how to control this. Okay, now, so let me tell you first an introduction what ITER, I think all of you have heard and you know ITER, but as you can see, the main idea of ITER is to produce these 500 megawatts of fusion power with a power amplification of 10. This has not been achieved so far in the magnetic fusion community. The record right now is with JET that achieved the 16 megawatts out of the 23 megawatts that were needed to get the fusion reaction going. And ITER, in principle, is supposed to be able to prove that it's possible to achieve this goal. It will take 10 years, the construction, maybe I would say a little bit more, 20 years of operation and 5 years of deactivation. Say that we don't talk about decommissioning. This is a peculiarity of the project because the decommissioning will be the responsibility of the host state. In this case, it will be France. So what I would like to make in the talk is to give you a situation, what is the situation with the ITER project, with the baseline, the design and construction progress, talk a little bit about the nuclear safety and licensing, which is a big achievement of this project, and I think for the fusion community in general. Not only for the magnetic community, but I think in general for the fusion community, nuclear fusion community. ITER is in principle designed to, as you can read here, to produce a plasma dominated by alpha particle heating, and this is a key element. Until now, all the machines in magnetic fusion are being dominated by external heating. This will be the first machine that will be dominated by the alpha particle heating. It should produce, as I mentioned, a significant fusion power amplification factor, a factor of 10 in long pulse operation, meaning more than 100 seconds, and aims to achieve a steady state operation of a tokamak, these pulses with thousands of seconds, but with a Q, with a gain factor of about 5. The possibility is retained that in the second phase of the operation, the possibility of exploring the control ignition of Q bigger than 30. This from the point of view of physics, but in technology is very key for the good operation for the development of fusion, to demonstrate the integrated operation of all technologies, well, not all, but most of the technologies that are relevant for a fusion power plant. We will test components that are required for this fusion power plant, and then some concepts for the tritium breeding module, even though this is not going to be one of the big elements of ITER. It's a huge project, I don't have to tell you that, and one of the good things is about the collaboration aspect. You know, in ITER is, we have all the 50% of the population is represented in the project with the participation of the US, EU, European Union, Russia, China, India, Korea, Japan, and about 80% of the gross national product of the world is represented by these countries. It's very peculiar because, as it is mentioned, 90% of the components are going to be supplied in kind by the parties. This is a very good aspect of the project when you are taking into account let's say the agreement to build the project. Governments like very much this in-kind contribution. From the point of view of management, this is not so easy. I have to tell you, and the experience have shown that is something that makes things life a little bit more difficult. Interfaces are growing a lot between all the parties. The distribution that was done, as you can see here in this transparency, you can see in the horizontal axis all the members, in the vertical axis the different components, and you can see that all members in the country, in the project, somehow participate in most of the components of the construction of the components. That certainly is not the most efficient way to build a car, where every wheel is built by a different company, but certainly is very good from the point of view of collaboration and from the point of view of putting together all this effort between all these members. But this is a very peculiar thing in the management of the project. We are making this transition from design to construction. I hope to convince you about that. About 80% of the contracts, the agreements that we have with the domestic agencies, every member has created a domestic agency that is responsible for providing these components to the ITER project, to the IO, as we call it, the ITER organization. And about 82% of the in-kind value has been already committed and signed with the different domestic agencies. Here you have several, in some pictures of our Director General, Professor Motojima, with some of the domestic agencies, the US and Japan and so on. The production is ongoing of most of the big components of the elements that are components that are in the critical path of the project, particular conductors of the vacuum vessel and so on. I will tell you a little bit more of details about that. But the production is certainly ongoing. So, as you know, ITER, this is a cross-section of the machine with the main parameters of the project. It's a huge project, so almost 1,000 cubic meters in the vacuum vessel, 130 cubic meters to be exact. The idea is to produce, as you know, a very magnetic configuration with a D shape, which has been proven to be the most efficient, one of the best in the community. It's very similar to JET, those of you that know this machine. And the main characteristics are given here in this transparency. We'll work with the introduction in the upper part of a mix of deuterium-tritium. That will be our fuel. We are not going to produce the tritium in ITER. That will be left for the demo machine. Only a test of this capability will be in some what we call test blanket modules. But certainly in our case, our blanket is simply a neutron absorber. We have to protect the superconducting coils from this neutron flux, and therefore we put this what we call blanket modules to protect the machine in there. With the help of the auxiliary heating that we will also use, mainly microwaves or different ICRH also, we'll get to the to the heating of the deuterium-tritium, to the thermonuclear temperatures to produce the helium and the neutron. This helium we have to extract from the machine, so we need something to extract the helium in all the impurities that are going to be present from the plasma wall interaction, and that we do through this key element, which is what we call the diverter, to have the particle and heat exhaust, where all the concentration of the heat will be done mainly in this part of the machine. The parameters that we are aiming are of these values, very low density, 10 to the 20, compared certainly with inertial densities. Peak temperatures similar, 17 kilo electron volts, fission power 500 megawatt. Plasma current will be, in principle, nominal 15 megaamp. I will tell you a little bit more. In the licensing process, we achieved that in principle we could go beyond 15 to 17 megaamp. And the toroidal field will be this 5.3 Tesla. So the main components that we have to construct are certainly all the magnetic configuration with the central solenoid, toroidal field coils, poloidal field coils. All of them superconducting, so we need to put them inside a big refrigerator, the cryostat. We need this vacuum vessel for the production of the fusion reaction, and also is our first confinement barrier from a nuclear point of view. Then the blanket modules I mentioned to protect all the holes, the superconducting coils and the rest of the machine. The diverter, that is the key element for the extraction. Some internal coils that to control the plasma further. These were introduced in the last design review that was done at the very beginning of the project in 2007. Thermal shield to protect the cryostat and so on, and some correction coils to take care of the difficulties we will have certainly during the construction. The status of this of the machine, of the main components you can see here. The cryostat is a huge, maybe the biggest refrigerator built in the world right now. It's a stainless steel machine, 304L stainless steel, 3,500 tons, and this is being built by India. The procurement arrangement was signed in September 2011, and the construction, the signing of the contract with the company is being already done. You can see the dimensions. Sometimes it's difficult to see the dimensions of the machine, but when you compare with the very well-known Jefferson Memorial, you see more or less it's the same size. So we could use this site for the cryostat, but I don't think it will be a very good idea, finally. Magnets are certainly a big challenge. The size of these magnets and the performance and the energy that they accumulate, as you can see, is close to 50 gigajoules that will be accumulated there. The mass of this is really impressive. Only one of those coils more or less weighs the same as a Boeing 747 at full weight. And the production of the superconducting strand that you need in order to build these coils is also impressive. More or less now the whole niobium tin production in the world is dedicated to ITER. And already 409 tons, which means 85,000 kilometers of these strands have been produced, and this is about 90% of the total amount needed. So you can see that this is already very well on the way and finished. China and Korea have fabricated some dummy conductor to test the whole system. In Europe, also the production of the TF coil is going ahead with the different aspects in different places. Many countries are participating. Also in Japan, with several of the components related to the coils. 9 of these toroidal field coils will be built in Japan, 9 will be built in Europe. Actually 10, one will be the prototype that will be used as a spare. So this is why the production and you see all the countries that are related to that. Another key element that is in the critical path of the project is the vacuum vessel. to call it vacuum vessel, when we discussed this with the nuclear fission people, they look at this and they didn't think that this was exactly a vessel in the nuclear term. As you can see, it's more something with a lot of holes. But certainly this is a key element for the demonstration of the safety of ITER. It's an impressive vacuum vessel, also 8,000 tons, heavier than with the in-vessel components is 8,000 tons, heavier than the Eiffel Tower. You know, we are in France, so we have examples from there. This is a very peculiar element, and as I said, a very key element for the safety demonstration and for the good working of the machine. It's a double wall stainless steel machine. You have here the main parameters, almost 20 meters outer diameter, 5,300 tons, the vacuum vessel itself. The vacuum vessel, this is a typical example where you see that it's not you would not design a project where it's built by sectors. 2 of these sectors are being built in Korea, 7 of these sectors are being built in Europe. Certainly with different companies and even in some cases with different technologies. So from a management point of view, it's not so easy, but the whole idea of this project is when it is finished, any of the members in principle can have all the information in order to build a future reactor, a demo, if they so wish. But the vacuum vessel is the key element for the defense of safety in fusion, in magnetic fusion. And this is a very peculiar because the loads that are, when you analyze a machine like ITER, and it's been from the point of view of getting the license, the loads that the nuclear regulator is used to are not exactly the same. The main loads that we have in our vacuum vessel are the electromagnetic loads. And these electromagnetic loads are not exactly very well known to the level that typically is known in the nuclear fission industry. So it means that we have to build a lot of margins in order to take care of these uncertainties that we may have. So you can see here that our machine, this is a kind of a representation of our margins. We define a core, a hard core, where this is where all the safety demonstration is given, and that implies the maximum current in the plasma of 15 megaamp. But we do have considered the possibility to go to up to 17 megaamp, and you see that there's still, even going beyond 17 megaamp, we have built a margin of 50% in order to get the possibility of forces of almost 70 meganewtons that could be still going to the break limit of the machine. That is, at this point, totally needed in order to be able to license a machine like ITER. The construction is going on right now. In Europe, this is a mock-up of one part of to show the electron beam welding, the success of that, and also in Korea, as I mentioned, where they are more advanced in the construction of the vacuum vessel and also of the thermal shield. A key element also for the protection of the whole system, people and the machine itself, is the blanket. That is to provide mainly, well, not mainly, but one of the big reasons is to make the neutral shielding of the superconducting coil. Also to extract the heating from the machine is done through the blanket. But as I said, in ITER there will not be production of tritium, only very small amounts in test blanket modules. We have 440 blanket modules. This is where it is concentrated, the interaction of the plasma with the first wall that will be made of beryllium and tungsten. The divertor finally will be, well, it's not been decided yet, but it's very likely that it will be only tungsten divertor, and the wall will be a beryllium wall. This is being tested also in the environment of JET with exactly the same components for the first wall, which have very good plasma wall interaction properties. The main concentration of heat and particle flux will be done in the divertor that, as I mentioned, will be mainly, most likely, will be only a tungsten divertor. The main reason, or one of the main reasons, is also has to do with safety and with the licensing process, because initially it was considered the possibility to have a carbon divertor, much better known in the community, in the tokamak community. But the problem with the carbon is that it gets absorbs tritium very well, and it's not so easy to get rid of to deabsorb the tritium. So with tungsten, we have the possibility of have it bakeable at 350 degrees, and the possibility to degauss the gas, the tritium, makes the whole safety issue much more easier. Each of these vertical targets is made of these rows of individual plasma phasing units with all of them cooled. They have been tested in Europe and also in Japan to the values which exceed the requirements with 20 megawatt per square meter in 1,000 cycles, as you can see here. So the technology is actually there. I mentioned that there will be a few test blanket modules to test the idea of how to produce tritium using the neutrons that are going to be produced in ITER, but this will be only very, very limited. The ITER site, after it is constructed, should look something like that. This is a huge site, 1.4 kilometers long, about 1 kilometer wide. I invite you to come. It's really impressive when you see there. And the construction is going on right now at a very good pace. The headquarters was inaugurated in January of this year. We are in a place where the seismicity is relatively moderate, but enough to have a system of protection where the whole machine is going to be on a 493 columns will give the seismic isolation of the whole machine. You can see here the work that is going on in the assembly hall. They're putting the concrete already in the assembly hall. And very large contracts are already being given, some of them to like the cryo plant that we are going to produce. I think it's going to be the second biggest in the world after the CERN one. There is also a big contract with a Spanish company, ENSA, to give for the welding of the vacuum vessel, which will be, as I mentioned, a very key element. Or here you have also some of the structures of the TF coils that have been constructed not so far. The construction of the big building was given to a consortium that started the work only a few weeks ago. And this is a very, very key element. This is the second confinement barrier, so from a nuclear point of view, is also one of the key elements. And that takes me to the nuclear licensing. See, for those of us that work in the fusion community, this is something that normally this is not even thought about. You say, no, safety, fusion is safe, it's inherently safe. Okay, very good, yes, okay. But now prove it. It was never proven before. This is always the fusion community that made the analysis and said that this proof had to be done. And even the fact that ITER was considered as a nuclear installation sometimes was even thought that why you need to have something like that. But the fact is that we have a tritium inventory, a radioactive inventory, which is very significant. And to give you an idea, in France, if you are beyond 27 grams of tritium, you are considered a basic nuclear installation. Basic nuclear installation is a big name that includes the nuclear power plants or includes something like ITER. Because in ITER we have in the order of 4 kilograms. So 4 kilograms, as you can see, is orders of magnitude bigger than the limit that you have to be considered a nuclear installation. Also, we do have, and this is a reality, activated products. We have these 14 MeV neutrons that are going to activate our cooling systems, elements in the tokamak, production of corrosion products, and so on, just like most or any nuclear power plant. And we are going to produce waste. Certainly, we are not going to produce waste of the same characteristics as a fission plant, but meaning we are not going to produce waste of high activity, long life, but we are going to produce waste of low activity and medium activity. Some of them tritiated, which is also not so easy to deal with by the different groups and systems that are going to handle the tritium. But the very good thing, I think this is something that this is a lesson that, in my view, one of the key elements for the future of fusion. The very good thing is that we have been able to prove, and it has been accepted by the Nuclear Safety Authority, that there is no safety function associated to the control of the fusion reactions. And this is a key element. Because when you go into a nuclear licensing process, if you have to demonstrate that your safety depends on the behavior of the plasma, then you do have a problem. I can tell you, you do have a problem, because there is still a lot of unknowns in the knowledge and in the control of this fusion reaction. To give you an example, disruptions do exist in the tokamak, and we know that they are going to happen. And the second thing, that there is no safety function associated to the power dissipation, the cooling systems. Your cooling system can fail, and still there is no safety issue associated to ITER, or in this particular case to ITER. And I think that these two functions, for the future, they should be maintained like that. Otherwise, it will be much more difficult to control and to license any fusion machine in the world. The two safety functions that we have is the confinement of the radioactive materials, that they do exist, and the limitation of the radiation exposure to people and to the environment. In order to prove that, we had to go through a full safety analysis, analyzing all the internal risk and external risk that we had. Many of them very traditional, like fire, explosion, internal explosion. We are using hydrogen. The hydrogen may explode. We have a lot of dust in the interior of the vacuum vessel, so the dust may also explode. Thermal deviation, plasma transients, some not so key, like plasma transients or the magnetic and electromagnetic perturbations, and also external risks that could happen, seismic, extreme climatic conditions and so on, fire, plane crash and so on. So we had to go through a full list of design basis accidents. As it was mentioned in the talk yesterday by Professor Rubia, this was not done in a probabilistic way. Certainly it cannot be done because there is no experience on fusion, so it must be deterministic, and we went through a full analysis of this design basis and beyond design basis. Accidents where the possibility that this could happen, or combination of accidents without any interaction between them, to see and to test the limits of the machine. And that was done in a very thorough analysis by the Nuclear Safety Authority in France, which I think it can be said that is one, if not the most strict nuclear safety regulator in the world, through a very difficult process that took, as you can see here, more than 2 years. Actually, it took a little bit longer because we started before that, with a process that involves the public, with the public had the opportunity to check all the safety files that existed in ITER, give their advice, their complaints, their recommendations, and a thorough analysis, a technical analysis with the technical body of France, the nuclear regulator is called IRSN, the Nuclear Safety Radio Protection Institute, with meetings almost every week that analyze the whole machine, all the conventional, non-conventional aspects of the machine. And again, I think if those of you that were in the talk talking about the emerging systems and by Professor Rubia, he did mention that one of the key elements of fusion, DT fusion, and one of the challenges will be to how to handle the tritium and how to prove that to the regulator and to get the license. Okay, so we can say that problem is solved. We already did it. This, for the very first time of the fusion community in nuclear history, this has been done. And now there is a decree that was signed by after all this whole process, by the Prime Minister in France, is the process, the administrative process, that is the conclusion of a very thorough, I insist, an independent analysis of the safety of ITER that says, yes, the risks are manageable and you can go ahead and build the machine. This, in my view, is a historical development for the fusion. Never before happened, and now we can say that this is possible and it has been accepted by a nuclear regulator. So with that, more or less, with that positive feeling, I want to conclude. I hope to convince you that you see ITER is now very well in its way, with a lot of difficulties. I don't want to hide that there are a lot of difficulties. We do have difficulties with the schedule of the machine right now, also with the cost. The cost has been increased since it was originally designed, but is very well underway, and the situation right now, I think we have this flexibility to meet all the challenges that this project is going to have. So thank you very much for your attention. Don't know.
Thank you very much, Carlos. I think we have, certainly you have a lot of questions, but we have time only for one or two. Okay. Wait. Octavio. Just move up.
Okay. Thank you, Carlos, for the overview of the construction and also the licensing. I have a very short question, only two questions, very short, but are related. The first one is, if this installation justify to have 10 years construction, 20 years operation, and the second one is the licensing is just for all the time of the operation of the ITER?
Okay. Well, the first question is justified these 10 years. Certainly, I can tell you that from the experience that we had, it took longer. People did not realize at the very beginning that to go from a greenfield place and to construct the whole project itself, that took longer than the people expected. But I think there was a clear underestimation of that. The whole organization of how the project, as I mentioned, is organized with the 7 domestic agencies is not optimum to go fast. You have to take into account, and this again now has been realized. We have produced now what is called the Unique ITER team, where we try to put together the heads of the 7 domestic agencies with the IO in order to speed up the decision process. So I think it can be done much faster the construction. I fully agree with you. 10 years, I think is a maximum. But now that these things are realized for the future, I'm sure that this will not be the case. The licensing process, yes, it is for the whole life of the project. It goes from we have in the decree, we still did not get the technical prescriptions. They will be given to us most likely in a few days. But it goes from the phase of design, construction, operation, and decommissioning. There will be many additional steps that we have to show and many whole points that we have to tell them. We produce the so-called preliminary safety report. This will have to be upgraded as the project progresses for the future, but yes, it covers the whole project.
Thank you. Very short question, please, because we have started late.
After the Fukushima accident, the French safety authorities invented the concept of hardcore or hardened kernel. I don't know how to translate it in English, which is an ensemble of material and organizational dispositions designed to resist the unthinkable event. The implementation of this hardcore to French nuclear installations is underway. It will cost the country of the order of 60 billion euros. And I would like to ask, how does this concept apply to ITER?
Okay. This was actually one of the issues that we had. If you see on the dates that I mentioned for the licensing, we had the so-called l'enquête publique, public inquiry. We launched that 3 weeks after Fukushima. So you can imagine the environment on which we did this enquête publique. That was a big challenge for the whole project. The good thing, so that meant that during the technical evaluation that we had with the IRSN and ASN, Fukushima was already taken into account during the Group Permanent. We took the advantage that, as I mentioned, due to the characteristic of the project, we went from a deterministic process, deterministic analysis of all the possible accidents and so on. So somehow, all what was later on requested to the different components, to the different power plants and so on after Fukushima was already built in the analysis that was in our case. We took and we have gone through this process of Fukushima analysis, and actually we have sent all the information to ASN. And in 2 months, at the beginning of July, we will have the meeting of the Group Permanent to finally give us the conclusions that they will of the Nuclear Safety Authority. But the expectation that we have is, due to the robustness of the main issue, that is the combination of seismic events with inundation and so on, that fortunately in our site is very well protected from that. We took it into account already with the destruction of a dam that exists north of Cadarache, a combination of a seismic event beyond the... Right now our machine is designed to withstand more or less the biggest earthquake in the area of Cadarache is 5.3, given in Manosque, which is a city very close to Cadarache. The machine is designed to withstand a seismic of magnitude 7 in the Richter scale, but the integrity of the building goes to beyond 9. So we had good confidence that this process is not going to finish with any big impact in our noyau dur, the definition of the noyau dur, the hardcore that they are going to do. We hope that it will be quite light. But I cannot tell you for sure, it will need 2 months to get the result.
Very good. So here we close your talk. We thank again the speaker, Carlos. Thank you very much.